Hello, everybody. I'm Sanjay Junturkar from Oracle. I'm Senior Director managing the HeatWave team. I'll be doing today's presentation along with Sandeep Agarwal, my colleague at Oracle, and Pablo Lemos from Tetris. Today, we'll be talking about in-database machine learning with MySQL HeatWave. Here's the agenda. I'll go through the motivation, give a quick overview of HeatWave ML and its usage, and at that point, I'll hand it over to Sandeep, who will cover the technology. He'll compare it with one of our competitors, specifically Redshift ML, and then do a short demo. Here's a typical machine learning process. It has three separate parts to it. The first part is to train or build a model using historical or training data which is sitting in the database. The second step is to do prediction or inference based on new data which is also resident in the database. And finally, to understand the predictions and inferences, one can use various explanation techniques. And these will essentially inform the user as to why a particular prediction was made the way it was made, whether it's good, bad, or ugly. And HeatWave ML provides you the ability to do all these three things inside the database. Now, let's look at how a user would have done machine learning before HeatWave ML was introduced. The user's data is sitting in the MySQL database. To do the training, they would have to pull the data from the database onto their machine, pick an algorithm which would be used to do the training, generate the model, then do an inference on fresh set of data which is also resident in the database and it would have to be pulled out, and then do the ML explanation. Now, this approach has a couple of problems. First, from a governance and security standpoint, the data has to be extracted from the database onto the user's machine, which could be a problem in itself. Secondly, the user has to be familiar with basic ML concepts. They have to be familiar with the algorithms that are available for a particular task at hand. They will have to familiarize themselves with which features to train on, which hyperparameters to tune, and which algorithms to choose. Also, they will have to familiarize themselves with the pre-processing steps that they will have to undertake. In addition to that, they have to become an expert at Python because most of the ML frameworks are written in Python. And last but not the least, they will have to pay the cost of doing the training on their own machine because that's where the work is being done. So that's the issue with doing ML training on user's machine. We have solved that problem and we have addressed that problem by moving those things into the database. And by that, I mean the training, the inference, and the explanation, all of that is done inside the database. And the user has to issue queries to do these three steps. And I will go through those later. Now, it solves a couple of things. One, the data does not have to be extracted onto the user's machine. Secondly, the user does not have to become an expert or does not have to become familiar with which algorithms to pick, which hyperparameters to tune, which features to train on, so on and so forth, because all those things are taken care of by HeatWave ML automatically. HeatWave ML will automatically pick the appropriate features to train on, the appropriate algorithm that is best suited for the task. It will automatically pre-process, so on and so forth. All of those things are done automatically. All that the user has to do is issue the appropriate queries. Now, note that they also won't have to become familiar with Python here because these queries would have to be written in SQL. We provide a very easy SQL interface to do that. And last, given that training is being done inside the database, they do not have to pay the additional cost of doing the training on their own machine. Thus, there are multiple benefits to doing this within the database, which is what HeatWave ML provides. Now, in totality, if you look at HeatWave ML, it's a fully managed, highly scalable, and a cost-efficient machine learning solution. There is absolutely no need to extract the data from the database or the models for that matter onto the client's machine or the user's machine. The interfaces that we provide are very user friendly, and we leverage the existing HeatWave cluster to do the training. Also, we provide model agnostic explanation techniques, which can essentially explain out both the model as well as the prediction behavior. Now, if I were to take a step back and look at MySQL HeatWave in totality, then this is the only MySQL service which does OLTP, OLAP, and ML in a single in a single service. There is no need to do any ETL. The training, inference, and explanation are all done within the database, and there is no need to learn a new language or a new framework like Python. Now let's look at the target use cases and personas. From a target use case perspective, we are currently targeting 3 separate categories. One is classification, regression, and time series forecasting. Classification is where we do predictive modeling so that a discrete category can be predicted for a given input data. In regression, we predict a continuous value for a given input data. And for time series forecasting, a trend is predicted. So currently, these are the things we have in our feature set. And many more are coming in future releases. From a persona perspective, we are primarily targeting database users. For them, we provide a very easy and familiar MySQL interface so that they can use the service. And then also provide, using HeatWave, a very good baseline model that they could use. In addition to that, lately we have also provided certain hooks so that data scientists and machine learning developers can also use the service. They get a basic model to bootstrap themselves, and after that they can do continuous experimentation with it. So for instance, we provide settings which are tweakable so that they can decide which particular features or columns from the dataset to use and which ones to exclude for training, or which algorithm to include or exclude from consideration for developing the model. Similarly, which particular optimization metric should they use for the pipeline to optimize the model on. Things of that nature we have introduced so that it becomes, it's also useful for data scientists and machine learning developers. One other thing I want to mention is the explainability part. As I said earlier, we provide both model explainability as well as prediction explainability. For model explainability, essentially, it will give you or the customer an ability to see which feature was most important for the model. Thereby, you can get a deeper understanding of why the model behaved the way it behaved. From a prediction explainability standpoint, customers can see which features were important for a particular prediction, not the entire model, but just their particular prediction. Now let me look at some of the interfaces that we have provided. Essentially, we have 3 separate calls, one for training, one for prediction, and one for explanation that I will go through. The sysml train call essentially takes the table of data on which training has to be done, the name of the column that has to be predicted. It takes an optional JSON argument to decide whether it's a classification, regression, or forecasting task. By default, it's a classification task. And then it returns a model handle. One can use that model handle in the predict table command, which is basically predicting on a set of data. So this is the name of the table to predict on. This is the model handle that we got in the first step. And then this is a table where the predictions are stored. So that's what predict table will give you. We have another command, which is explain table. And what that does is take the table on which you need the explanations on, takes the model handle, and then it also takes the table in which the explanation should be stored. So this is very straightforward, very easy to use, and that's what end user will have to have access to. With that, I will hand it over to my colleague Sandeep, who will go through the details of the technology and then do a competitive analysis as well as a short demo.
Hey everyone, I'm Sandeep. Thank you, Sanjay. So as Sanjay has talked about, Training within HeatWave is fully automated, which means it requires no user input. And the way we can do this behind the scenes is by using a technology called automated machine learning or AutoML. So the way this works is we take your data or your table, right, and feed it to this AutoML pipeline. This consists of multiple stages. So we take your data, we identify all the null values in this data, and then we basically replace this null values by another value within your data. And we do this smartly. And values that we cannot replace, we drop. And similarly, after we are done with null value imputation, we then go ahead and identify all the string columns, such as char or varchar columns, and replace them with numeric values. This is because machine learning models require numeric data to train on. So this stage is called pre-processing. So after we are done with pre-processing on your data, we need to figure out what is the best algorithm for your data. The reason for this is there are a lot of different machine learning algorithms out there. For example, you have XGBoost, you have support vector machines, you have linear models, you have nonlinear models, and each one of them works differently depending on the data. So for your data, we automatically figure out what is the best algorithm that gives the best model. And this is called automatic algorithm selection. So after we have identified the best algorithm for your data, we then move on to identify an optimal sample size that works well for your data. This is because machine learning training is very compute intensive, and sampling the data is important so that training finishes in a reasonable amount of time. So we don't do this sampling randomly. We actually figure out what is the best sample size that works for your data. And by sampling, I mean both row sampling and column sampling. So we'll go into sampling and how it works into a bit more detail later. But essentially, the goal is to find the best sample size or the smallest sample size that we can get without degrading model quality. So after we've identified the best algorithm and the best subset of for your data, we then move on to hyperparameter optimization. So different machine learning algorithms have different parameters, and then we need to find out what is the best value of of those parameters that work for your data. And we do this by intelligently searching the entire parameter space. We try out different values, we figure out what parameters work well, what don't, and at the end of this, we basically have come up with a good model for your data. But we don't stop there. As Sanjay mentioned, explanations are a very key component of HeatWave, and we make sure that we can explain the models that we generate. So the first stage in explanations is basically we train the model explainer on the training data. So the goal of the model explainer is for it looks at the training data and figures out which features contributed the most to this model and which features did not. And once it has done that, it then moves on to prediction explanations. So prediction explanations are basically generated when you actually use the model to make a prediction. So the goal of the prediction explainer here is to look at the training data and learn the distributions of the different features in this data, and the distributions are later on used when you're doing predictions. So all this information is stored in the model, and essentially at the end of this, you get a tuned model out that you can use for your predictions, for explanations, both model and prediction, and so on. So now let's take a deeper look into what adaptive sampling does. As I said, adaptive sampling is something that we do automatically. We don't require the sample size from the user. We will figure out the best sample size for you. And the way we do this is basically for your data and the machine learning algorithm that was chosen by algorithm selection, we run through an iterative loop. So what this loop does is that we first identify a good sample size that works well. And then for this sample size or this subset of rows and columns, we basically train a model using the chosen ML algorithm and evaluate it. We measure the score. And then we keep iterating over this, trying larger and larger sample sizes until the score converges. So what this means is that any larger sample size will not result in improvement in the score. So this is how we make sure that we have picked the smallest sample that doesn't degrade model quality. So this is what we do in adaptive sampling. And of course, we do this while also making sure that we keep class imbalance in mind. So class imbalance is basically you have too many samples of a particular type and too few of another type. So when you're actually sampling, you need to keep into account that you don't miss out any samples of the lesser type and so on. Now, what are explanations? So let's dive a little bit deeper into this. So let's say you developed a model, right, using HeatWave, and you want to make sure that that your model is behaving as expected. You go ahead and deploy the model, and by deployment I mean you're going to use the model for predictions, right? You have new data coming in, or new, and you want to make sure that basically that the predictions make sense, right? And taking the example of, let's say, uh, a loan model, right? A model which predicts whether a loan is approved or denied based on a particular customer, right? So explanations allow you to give you insight into what was it about that customer that caused that loan to be approved or denied. For example, like, was it the customer's checking account balance, was it their age, was it their occupation, and so on. So this helps with regulatory compliance. A lot of countries nowadays have a legal requirement for a right to explanation. So if you're going to use a machine learning model to give a user some decision, the user is entitled to an explanation for that decision. They of course allow for fairness. So going back to the example of the loan model, right? So if, let's say, the model explanations say that the gender of the customer was an important factor in predicting whether they get the loan or not, you need to basically fix that. You need to make gender should not be important, and that's how you ensure fairness. Similarly, the model should be repeatable, and you need to ensure causality. This means that the explanations that come out of the model need to make sense. For example, you need the explanations will tell you whether the model learned on something completely which it should not have learned on. Then you need to go back and revisit training data. This also allows you to build trust on the model, because then you need to that makes sure that what the model is learning is valuable and useful and makes sense. Now, explanations are a key component of the HTML pipeline, and we support both model and prediction explanations. So model explanations are generated, as I mentioned earlier, during model training. And the goal of model explanations is to look at the training data and, as a whole or globally, look at what features mattered the most. Was it the customer checking account balance? Was it their age? Overall, what was important? And then similarly, prediction explanations, they look at each individual prediction and then figure out for that particular prediction what mattered the most. And to give an example, let's say you have two customers, right? Customer one, customer two. And let's say customer one's loan was, and let's say both their loans are predicted to be denied. But for customer one, the reason for the denial might be too young, for example, and so on. And for customer two, maybe the checking account balance was too low. So this is where model prediction explanations can give you deeper insight into each individual prediction, which is different from model explanations, which give you an overall insight across customers. And HeatWave can explain all classification and regression models, and they're fundamentally integrated into a training pipeline. Now, we have added a lot of new explainability techniques in 8.31, and let's look at a few of them. So we had HeatWave users now have the ability to train Shapley explanations. So we actually allow the user to compute full Shapley values. Shapley values are actually a theoretically sound approach to compute the correlation between, or the contribution of a feature to the result of a model or to a prediction. So HeatWave actually supports fully distributed Shapley values across an entire cluster, and it can be computed very quickly. The other explainability technique we've added is PDPs. What PDPs allow you to do is to visualize the correlation between a feature and the target. To give you an example, coming back to the loan model, you want to understand how the age of a customer influences their chances of getting approved, right? So on the y-axis you have the basically age of the customer, and on the x-axis you have the age of the customer, and on the y-axis you have the probability of the loan getting approved, and you can visualize how the changes in age change the probability of the loan approval. Now, another thing we have added recently is FastShap. Now, FastShap is a novel technique that was developed within Oracle. It is a very, very fast alternative to SHAP, and it actually gives you explanations which are almost as accurate as SHAP. So we evaluated FastShap on a variety of data sets and compared it to SHAP. So the table of a year on the right shows you this comparison. So the correlation basically on NDCG tells you how close were the explanations of how to generated by FastShap to SHAP. And the closer they are to one, the more accurate they are. So here you can see that for both classification and regression, the NDCG is more than 0.99. It's really high. So these are really accurate explanations. And The runtime is almost like an order of magnitude less than Sharp. So fast Sharp can actually give you explanations for even for very large data sets in like several minutes or so on, and it's really fast. So for classification, you're getting more than an average speed up of 12x, and for regression, is actually you're getting a 56x speed up over Sharp. So this technique is very accurate and it is really fast. Now, in addition to classification and regression models, we have also added the ability to automatically train forecasting models. What is forecasting? So forecasting allows you to, for a particular feature, allows you to predict the values of this feature in the future. So there's always a time component involved. To give you an example, the chart on the right shows the electrical equipment orders for some particular company across a decade, and the goal is to predict basically what the orders will be maybe in the next few years. And as you can see here, the data is very noisy and it's really hard to make a forecast. HeatWave will intelligently break this down into different components which actually make sense. For example, the trend, which tells you whether the sales went up or down. The seasonality, which is basically, is there a pattern, is there a seasonal pattern across months in this data? And finally, the residual is basically whatever noise is there, because there's always some noise in the data, so the residual takes it out. So HeatWave will intelligently break these components and then find the forecasting algorithm that works well for your forecasting data, and that works well for these components, and also tune hyperparameters as we mentioned earlier. This gives you a very good forecasting model automatically without any input from the user. So now we can also train good forecasting models for you. Now, Heat2ML is very fast. Why, like, what makes it so fast? Let's have a brief look into architecture. So on the left side, you have the client. The client is basically what users use to log into the MySQL server. So the client sends that, let's say, a training request to the server, and the server actually what it does is that it distributes the training request across the entire HeatWave cluster. So we have a scheduler node and we have multiple worker nodes. So what HeatWave does is that every stage of the pipeline exploits both inter and intra-node parallelism. This actually allows us to basically parallelize across, exploit massive parallelism, making your training really, really fast. Now, those were we have covered a few of the important features of HeatWave. Now let's look at how it performs against Redshift ML. So we took a variety of datasets from open source. These datasets spanned a variety of domains, different number of features, different number of rows, and so on. For example, we have Higgs, which has more than 10 million rows. Similarly, we have MNIST, which actually has almost 785 columns. And then we trained models on HeatWave and Redshift ML, and we compared the scores, the runtime, and the cost of training. And this is for both classification and regression. All these data sets, all our code is available publicly on GitHub. You can actually download it and run this benchmark yourself if you want. Now, the results are amazing. HeatWave on MDS is actually significantly faster than Redshift ML. And how fast? On average, 25x faster, which is like an order of magnitude higher. So the figure here shows basically on the x-axis you have different data sets. The red bars are basically a summary of classification and summary of the regression data sets from the table in the previous slide. And the y-axis is actually in a log scale. So these are really high speed up. So basically we have the speed up is basically the comparison, the training time between HeatWave and Redshift ML. The other thing to note is that Redshift ML, some of the datasets are so varied, right? They have a lot of features or so on, or they are too large. Redshift ML can only successfully train a model on only 14 out of 18 datasets, where HeatWave can do this on all datasets. The other key part of why training, what fast training buys you, is that it makes you basically allowing retraining very easy and cheap, right? Because this allows you to that whenever new data comes in, you can keep retraining your model, making sure the model is up to date. Training doesn't have to take a very long time, doesn't have to be too expensive, or so on, which improves overall prediction accuracy. Now, speed alone isn't everything for machine learning. The accuracy of the model also matters. And here also, HeatWave ML is as accurate as Redshift ML. So the chart on the bottom shows the score achieved for different classification regression datasets. And basically in almost all cases, HeatWave gets a similar score as HTML or actually higher, which makes a classification geomean accuracy of 0.754 much higher than the 0.712 for HTML. Now, we looked at the runtime. HTML is really fast. HTML is as accurate. What about the cost? This is where true savings come in. HeatWave is much cheaper than Redshift ML. And how much cheaper? On average, it costs a 6 cents to train a classification model on HeatWave ML versus almost $6 for Redshift ML, making HeatWave ML 100 times cheaper. That's a big deal. And this, because it's so cheap to train a model, like just 6 cents, you can actually just keep training a model again and again. And that allows you to have a much faster model development process. It makes your model much more accurate because you can train it more frequently. You don't have to worry about the cost anymore. And even for regression, it's almost 50x cheaper. So we we looked at the runtime, we looked at the score, we looked at that it's really cheap. Now let's actually look at a live demo for E2ML running on one of these data sets, specifically bank marketing, which is in the table earlier. So bank marketing is basically data gathered by a Portuguese bank. So what they did is that they made a bunch of marketing calls to their customers, and the goal of those calls was to sell a product. And so they recorded different attributes about the call, like the duration of the call, the month the call was made in, the day it was made, the customer checking account balance, the customer's age, and so on. And the goal of the model is to predict whether the customer will buy the product or not, or whether the call was successful or not, basically. And that's what we're going to do in this demo. So now let's move on to the demo. Thank you. Okay, so we have this Jupyter Notebook. Jupyter Notebook basically allows you to run Python code. It's a very popular tool used for machine learning. It's it we, this is already connected to an existing MySQL DB system, which is connected to a 4-node HeatWave cluster. So this execute SQL function is a Python function that allows you to run any SQL query and gives the result back as a pandas data frame. So we first look at the training data. So this is training data. Like these are the different. So this basically describe bank marketing train. These are the different columns and their types. And as you can see here, basically you have the customer's occupation, their marital status, their education, the checking account balance, the month the call was made in, the duration of the call, and so on. Why here basically is the target variable, or basically whether the customer bought the product or not, or whether the marketing call was successful or not. So let's train a model in the HeatWave. So Sanjay went over basically the different APIs we have. So the training API allows you to quickly train a model on this data set. So we give the name of the table, the name of the target column, which is Y. The task is that we want HeatWave to perform this classification. And then the resulting model will be stored in this variable, which we pass in, which is the session variable called at model. So we run training. Following training, we then load the model onto the HeatWave cluster. So this is the model which was trained. And training, basically, as we discussed earlier, runs really quickly. It runs on the HeatWave cluster. Everything is distributed, and this table has 30,000 rows, which is quite large for machine learning. And then even for that, the model got trained in like almost 3 minutes, which is like really fast. And then following training, we then basically go ahead and train the explainers as well. So here we are training the permutation importance explainers for both model and predictions. Similarly, you can, as we talked about earlier, you can also pass in sharp or fast sharp as options here to train different explainers. So after training is done, we want to know how well the model did. So this is called scoring a model. So what scoring does is that you have some data which we call the test data. This is data the model has never seen before. This is essentially mimicking a deployment scenario where you have new calls being made and you want to predict whether the basically the customer bought the product or not. The only difference here is that we know the result beforehand, because this allows us to score the model on data it has never seen before. So this data contains the column Y. And essentially what we're doing is making predictions on this data and comparing to the actual Y to see how accurate the model is. So this is what ML score does. It allows you to specify different scoring metrics. We support a wide variety of scoring metrics that are commonly used in ML. Here we are just looking at accuracy. So the accuracy of model, as you can see, is pretty good. The model is like 9. So this is basically a value between 0 and 1. So here the model is more than 90% accurate, which is a very good model. Scoring is also happens in like almost 3 seconds, which is really quick. So the other functionality, as we discussed for HeatWave is the ability to generate explanations. So one of the first things we do is look at model explanations. So HeatWave maintains a special table per user called the model catalog. So all generated models are actually stored in this catalog, where each row is one model trained by a user. So this also includes metadata about the model, such as explanations, the training table name, and so on. So we select the model explanation. So this is a very simple SQL query. Select model explanation from this my catalog. Admin is my username, where this was the model. So you basically ask like, look up the model handle, which was trained earlier, and get me the explanation. And then all we doing here is basically getting the explanation out, parsing it in JSON, and then plotting it using Pandas, which is a Python tool. So we show the model explanations here. So the chart here shows the model explanations. These are the different columns in your training data. And basically this is the weightage. So interestingly, the duration of the call turned out to be the most important. So the longer you talk to somebody, higher the chances of them basically buying your product. Month also mattered quite a bit, it seems. So that the month during which you make the call also matters quite a lot. So these were the model explanations, which your global view of the training data. And similarly, the other thing, as I said, the model catalog also stores a bunch of metadata. So you can also select to find out what exactly algorithm selection picked. So here, algorithm selection actually found out that XGBoost was actually a very good model for your data. This is also part of the model catalog. Now, we have looked at model explanations, we've looked at scoring, we've looked at training. Let's look at prediction explanations. So what we do here is we take a small subset of the test data. Let's take 100 samples and then basically mimic a scenario where you have a customer coming in, we make a prediction, and then we find out what mattered for that prediction. So here basically we're using the ML explain table utility, which allows you to make batch explanations, compute batch explanations. So we are generating explanations for these 100 customers using the model we trained above. And then we look at the explanations for this particular user. So these are the attributes of the user, right? So this was the duration of the call being made. This was basically, you have their age, they're 34 years old, they were married, and so on. And the model predicted yes, but that the customer most likely will buy the product. Why did the model say yes for this customer? This is because this is very well reflected in the notes column. We actually give a textual explanation for the explanation. So the duration, which was 486 seconds, actually had the largest impact towards predicting yes. So what this is trying to say is that because the call lasted for a long time, so around like 8 minutes, so this actually made this gives you a very high probability that the customer will buy the product. Whereas age contributed the most against predicting yes. So we also show essentially negative attributions. So what that means is that because the customer was young, the basically the model wanted to predict no, but because the call was very long, we also actually predicted yes. So the weightage of the duration of the call was much higher. That's why they compared to the weightage, the negative weightage of given by age. So this gives you a lot of deep insight into what's going on into your prediction, why the model predicted the way it did. So yeah, thank you everyone.